Mr. Sams is not here. We want to do the last podcast just by me, Mr. Bergmann. So I'm just going to kind of tie this one up here so we can get it going. We're a little behind schedule here. So I want to talk about the molar mass of gases. All right, so we can use the gas laws to determine the molar mass of a gas. So podcast 7.7, that's what we're going to talk about. All right. So what I want to do, molar mass of gas calculations, you could ignore this piece. First of all, we just need to understand what is the units on molar mass. If you recall, molar mass is the number of grams in 1 mole. And this varies. We usually look on the periodic table to determine what this value is. But basically, this kind of gives us an equation. If you know the number of grams, some number, and you divide by some number of moles, that will give you the grams in 1 mole. And so this essentially is the equation. Find the grams. The grams is something that's easily known. Usually you get this just from the mass data. It's easy to put something on a scale and weigh it. Or sometimes weigh a gas. Typically when you weigh a gas, you're weighing the lost mass, because gases usually leave a system. And to find moles, you're going to use the ideal gas law, PV equals nRT. And of course, N stands for moles. All right, mass can be measured on a scale, as I said here, and we can measure moles using the ideal gas law equation. So it's really pretty easy, okay? Really easy, okay? So let's do an example. 1 gram of a gas is collected over water. Now, when we say over water, we've got to play that water vapor pressure game that we talked about earlier, and it produces 250 mils of gas. What is the molar mass of a gas? Well, we're going to use this equation. So many grams divided by so many moles. Well, guess what? We know we have 1.00 grams. Sorry, I got interrupted. Okay, so now, so we know it's 1 gram, so then we just divide by the moles. And we've got some data here, pressure and a volume, go away, and a volume, and yeah, so we're going to use PV equals nRT. So what's our pressure? Our pressure is 572 torr. Now, I have to subtract the water vapor pressure. So we have to go to the water vapor pressure table. So I'm going to pause and go find that. So here's the water vapor pressure table. So at 25 degrees Celsius, the water vapor pressure is 23.7. So we're going to subtract this from the answer, 23.7. So that number was 23.7. But since this is rounded to the nearest whole number, I'm going to say 24. So if I subtract 572 minus 24, I can just do that in my head. That'll be 48 torr. Now I have to convert that to ATMs, remember? So there's 760 torr in 1 ATM. I'll get my calculator at the end here. And then my volume is 250 milliliters. All right, and I can then, there's 1,000 milliliters in 1 liter. I don't need a calculator for that. That's 0.25 liters. So that's my volume. And I think that's all I really need to know if I'm just find the moles. So let me get my trusty calculator out. So let's find the pressure. So I have 548 divided by 760 gives me 0.721. So this is, this is 0.721 atmospheres. All right, that's my pressure. So P is 0.721 times my volume, which was 0.25. I'm not going to put the units because it's easier. N is what I'm trying to find. R is 0.0821. I got my temperature, I guess. The temperature was 25 Celsius, but I can quickly add that in my head, or I'll do it over here. 273 plus 25. I knew it in my head, but just in case, it's 298. I'll divide both sides by 0.721 and 0.25. 0.721 and 0.25. These cancel here. And of course I did that wrong. I'm going to divide both sides by 0.0821 and 298. 0.0821 and 298, because of course the n was on this side of the equation. So I'm going to take 0.721 times 0.25 divided by 0.0821. I could have divided by r, which I saved earlier. Divided by 298 gives me 0.007. I'm going to move the calculator over here. So that equals 0.007. Now that's not just 7. I want to say 7, probably with 3 significant digits. Yeah, I must point 737 moles. Watch that. Remember, these two zeros here are not counted as significant digits because they're leading zeros. That's my moles. So that number is 0.00737. So now I'm going to take this, divide by this, and I'm going to have my answer. So I'm going to take 1.00. Technically, it's really just 1, really. Well, but it is a significant digit. Divide by 0.00737, and I get the molar mass is, look at the calculator, 130, let's say 6 grams in 1 mole. So that is the answer to this example. Okay, I think we're going to do one more example here. Let's move that over there. And hey, we got one more. Ibuprofen, the active ingredient in Motrin, has this many carbon, hydrogen, and oxygen. Analysis of this yields. What is the molecular formula? Now, this is a little more complex problem. Now, if I get percentage data, we're going to use an old axiom, percent to mass, mass to mole, divided by small, times to whole to find the answer. That will give you the empirical formula, and then we're going to use the molecular formula, or molar mass formula that I just did on the previous problem, and see if I can get this. So let's do the empirical formula thing first. If I can talk, Mr. Bergmann. Okay, Motrin, okay, 75.7 carbon. So when I say carbon and a percent to mass, I'm going to say 75.7 grams. And I'm going to convert to moles. There's 12 grams in 1 mole of carbon. So 75.7 divided by 12 gives me 6.3. 6.31 moles. Got that? All right, now I have hydrogen, and that's 8.7 grams. Now this is the easy one, right? Because there's just 1 gram in 1 mole. I don't need a calculator for that. There'd be 8.7 moles. And we have some oxygen, it looks like, too. So oxygen is 15.5 grams. And then I can say, of course, there's 16 grams, 15.99, 16.0 technically, in 1 mole. That's going to be a little less than 1. So I'll hold my calculator. 15.5 divided by 16 gives me 0.969, 0.969 moles. Divide everything by the smallest one. Well, that'd be the O, right? 0.969, 0.969, and 0.969. This one's going to be easy because that's 1. So I'm going to get the calculator to do the carbon. 31? 31 divided by 0.969 gives me 6.5. And this is 8.7 divided by 0.969 gives me about 9, right? Now, this ends in a half. So percent to mass, I did that. Mass to mole, that's this step here. Divide by small, times till whole. Since I have a half, I'm going to multiply everything by 2. So 6.5 times 2 is 13. I don't need a calculator. 9 times 2 is 18, and 1 times 2 is 2. So the empirical formula of this one will be C13H18O. That's just the empirical formula. The question is what is the molecular formula? Remember, you're going to take this and you're going to multiply by some factor. Well, we know some information about the temperature and all this kind of stuff, and we can determine what is the molar mass and compare it to this. So let's do that on the next slide. So if I have an empirical formula of C13H18O, I want to find the molecular weight. So I'm going to use the data that we calculated in the previous problem. All right, so we know the mass. So what's the mass? By the way, you should copy down this. I'm going to quick back here. It says that we have 0.25 grams of the substance, right? So 0.25 grams. I'm going to divide that by so many moles. I do not know the mole number, but I'm going to use PV equals nRT. So PV equals nRT. So what's my pressure? So my pressure, if you recall from the problem, it's going to be here 720 torr. Now I'm going to double check. Was it collected over water? It doesn't say it was collected over water, so let me do that. So if I take 720, I'm just going to do this quickly on the calculator. 720 divided by 760 gives me 0.947, 0.947. That's my pressure, times my volume. Now let's look back at the question. The volume was 23.6 milliliters. Now, hopefully you're getting to realize you divide by 1,000 to go from milliliters to liters. So that's 0.0236 liters is equal to N times R. Remember, R is our constant, 0.0821 times my temperature. I think it was 25 Celsius. We'll flip it back and find, what is the temperature? Mr. Bergmann can't see the temperature. 450 Kelvin. So it's 450 Kelvin. That's nice already in Kelvin, so I don't need to mess with that. Now, you algebra people, all right. Miss Purdue, how would I solve this problem? Come over here. Help me out. I'm not very good at algebra, so how would I solve for N, Miss Purdue? Miss Purdue just showed up. Miss Purdue, there you can see her now. What would you do here, guys? I want to solve for N. What would I do, Miss Purdue?
Divide by 0.0821
0.0821
and 450
and
Kelvin.
450. Yeah, that's what I do. 0.0821. I needed a math teacher for that one, didn't I? Not really, but just for fun. She showed up because I'm going to help her with some podcast stuff or DVD stuff. So on my calculator, what am I going to do? I'm going to take 0.947 divided by, times 0.0236 divided by 0.0821 divided by, remember you got to do divide because they're both on the bottom. That's a tricky thing, guys. And I get a tiny number. N is 6.05 times 10 to the minus fourth. Remember, watch that. If you see that right there, that makes important, that E. All right, so that's my moles. Well, that number is going to go up here. So if I take 0.25 grams divided by 6.505, pardon me, times 10 to the minus fourth, I'll get what? So 0.25 divided. Now watch the tricky, guys. I can say second A and S, which will type in this number, and I get a molar mass of 413 grams in 1 mole. So that's easy. Now, that's not the answer. This is the molecular weight. We need to compare it to the empirical formula. These problems can get long, can't they? So what's the weight of this? Well, this would be 12 times 13. Carbon weighs 12. There's 13 of them, plus 18. That's the weight of each hydrogen, plus 16, the weight of 1 oxygen. This adds up to 190. So that's the empirical weight. The molecular weight is 413. So if I take 413 and I divide it by 190, I better get a whole number or Mr. Bergmann messed up. I get 2.1, so it's about 2. So 413 divided by 2, or divided by 190, or say is 2. Close enough. And so that means this formula is off by a factor of 2, so I need to double it. So the real formula of ibuprofen is C26H36, I'm doubling it, O2. So that's the answer to this problem. And that is how we do molecular mass problems. You can see this is a very complex problem, but you'll be doing some of these in class. So we will see you in class, and we will make sure you know how to do these. Goodbye.